Okay, great. Well, good morning. So Mineral Physics 4 on modeling of planetary materials. And I thought I'd just start with a motivation, thinking of a planet as a sample, as an experimental sample. Of course, it differs in many ways from real experimental samples. It's much bigger, obviously. And also in the sense that its heat, temperature, and pressure are self-generated. So pressure is generated by gravitational self-compression, and temperature is generated by radioactive heating or the process of assembly or various other processes. But we can think about it as a sample in the following way. We can think about perturbing it in some way and seeing how it responds. And that response will depend on various material properties. And I give some examples here. So for example, we can see how our sample responds to changes in energy and input of energy, such as you might have from a giant impact, or heating from below, from the core, whatever. And the response will be a change in temperature, which is governed by the heat capacity, a change in density, governed by the thermal expansivity, and phase transformations in general will occur as well, possibly melting, possibly solid-solid phase transformations, depending on how much energy has been input. And that's governed by the free energy of the material. We can also think about how it responds to changes in stress. For example, the stress generated by an earthquake or an impact, and that will produce a strain in our planet, in our sample. That's governed by the elastic modulus. It'll produce a change in temperature as well in general, and the relationship between stress and temperature is governed by the Grüneisen parameter. And this will also generate phase transformations, changes in pressure. Deviatoric stress can also excite phase transformations, and again governed by the free energy. So how do we gather all this information together? How do we think about material properties of planets? And the guiding principle that I'll use today is thermodynamics, and the particular thermodynamic model that we've been developing and that you'll use in the practical later on. So just by way of introduction, thermodynamics, starting from the very biggest picture, it's the nice thing about thermodynamics is that its scope is so broad. You can apply it to the entire Earth's interior and the Earth's surface as well, much of the Earth's surface. You can apply it to other planets as well. You can even apply it to stars. It's been applied to black holes. This is meant to be a cartoon of a black hole here. Large planets, giant planets, most planets found so far, larger than Jupiter. We can apply it to those guys as well as our much smaller Earth. And, of course, to more prosaic objects as well. Thermodynamics is applicable to them as well. It's unusual for a physical theory in that it makes no quantitative predictions by itself. But what it does give you is powerful limits and relationships among various quantities. And what you need then is to combine thermodynamics with some other source of information about material behavior. And the sources of information that we've used are experiment and first principles theory. And what we've used these for is to guide two things: the functional form that governs the relationship among the various thermodynamic properties, and the values of the particular parameters, volume, bulk modulus, etc. Okay. Yes?
The other thing we've been talking about a lot, and we've talked about this. Sorry. Mark.
I'm not in practice here yet.
Mark, I was so slow for you. Sorry. What we have been talking about a lot, and asking our seismology colleagues for this help, is actually also understanding of the uncertainties in the system. Mm-hmm. And I actually think that there's some good value in trying to actually know what we don't know at the same time.
Yes, I agree, and I will address that a bit later. Yeah, the uncertainties, the limits of this approach. It's important, and in this context as well. I mean, thermodynamics is not magic. It won't give you the right answer by itself. any thermodynamic model is only as good as the material-specific information that you feed into it from some independent source, such as experiment or first principles theory. Wendy yesterday talked about experimental constraints. This is one of my favorite experimental slides. This is a chip of ringwoodite. We're looking down through the diamond. This is the gasket hole here. And this bit of ringwoodite has been heated with a laser in these spots here and transformed to this brown material, which in this case happens to be magnesium silicate perovskite and periclase. Okay, and another source of information about material properties that we've made use of and that is becoming more important, I think, in geophysics with time is ab initio theory. So this is a shorthand way of saying it is taking Schrödinger's equation and solving it and using that then to predict material properties. The reality, of course, is that you can't solve Schrödinger's equation for anything more complicated than a hydrogen atom. And so these methods are ab initio in the sense that you don't make any a priori assumptions about the nature of the bonding or whatever, but they're not exact. Nevertheless, they do have predictive power because there are no free parameters, no a priori assumptions about the nature of the bonding. As I mentioned, they do have scope, entire pressure range, temperature, pressure range of Earth and planets and stars, and people have applied it to this entire range and the entire periodic table as well. Accuracy is tested via comparison with experiment. And this is just one example here. These are the Hugonio curves of two liquids, diopside and anorthite, and the experimental data from Paul Asimo and his group are in the symbols here, and the density function, the ab initio prediction, is the curve. And of course, as you shock a material, as you compress it dynamically, you heat it as well. And so we're able to add information to this by calculating the temperature along the Hugonio as well.
Can you define Hugonio?
Yes, Hugonio is the set of thermodynamic state points that are achieved upon dynamic compression of a material. So in terms of a natural process, you can think of impacts. In terms of the laboratory, you have a much better defined geometry. You have some type of large gun that you use to fire a projectile at a sample with a very well-determined velocity. And as you hit the sample with higher and higher velocity impacts, you map out this set of thermodynamic state points, all of which together combine to make the Hugonio curve. And these are two examples here for two particular materials, starting from a molten material preheated to a liquid at 1 bar.
We'll come back to that on Thursday.
Good.
But meanwhile, the agreement in that graph is nice for both of us. It means either since we agree we're both right, or we're both wrong in the same way.
Yes. Obviously the former. Okay. So, okay, let's back up a little bit, and let's think about our planetary sample again, and think about the task that we have. Planets, of course, are not simple. They're not single materials. They're not a quartz crystal or even a silicate melt of a well-defined composition. They're messier than that. Planets generally have multiple phases in them. The phases, which phases exist, differ depending on where in the planet you look. And so one way of formulating our central problem is specify a pressure, a temperature, and a chemical composition at some point in a planet, and then figure out, calculate, which phases are present, what their compositions are, what their physical properties are, and then try to put all that together with some kind of composite theory, Voigt-Roycil or Hashing-Strickman, to determine the bulk physical properties of the rock. This is just one example of what might exist at a certain point in a rocky planet. This is a xenolith from Earth, obviously, and this comes from the garnet stability field. So you have red pyrope-rich garnet here. The sort of yellowish green are olivine crystals, and the Granny Smith apple green are clinopyroxene, and the black ones are orthopyroxene. So 4 different phases, very different compositions, very different physical properties. We need to be able to predict how much of each there will be, also what their compositions will be, how much magnesium, iron, calcium goes into the garnet versus the CPX, etc., and calculate the physical properties of each of those phases. That's our sort of task. And how are we going to do that? Well, the approach that we've taken is to base everything on something called the fundamental thermodynamic relation, a concept developed by Callan in his brilliant thermodynamics textbook, first edition from 1965. And what is this? This is a single function that contains complete information of all properties of all equilibrium states. Okay? So this contains all the thermodynamic properties that you might be interested in: heat capacity, thermal expansivity, density, elastic constants, etc. You can calculate all these from a single functional form just by taking derivatives of it. All the information is contained in that. So a very powerful concept. This functional form, there are certain rules about constructing these fundamental thermodynamic relations. So, for example, you can choose the relation generally takes the form of a thermodynamic potential or some kind of energy. So, for example, we could choose the Gibbs free energy for our fundamental thermodynamic relation, and it must then be expressed as a function of pressure, temperature, and composition. I'll be using n sub I, this vector, to describe the number of moles of each n-member species of each phase that we're interested in. So, for example, writing the Gibbs free energy as a function of volume, temperature, and composition doesn't work. Not fundamental, not complete information. Has to be pressure. We can also write the Gibbs free energy as a sum of the amount of each species times its chemical potential. And the chemical potential, in turn, can be written as the Gibbs free energy of the n-member, say forsterite if you're interested in olivine, or pyrope if you're interested in garnet, plus another term that contains all the dependence on the chemical composition of the phase. This is the gas constant times temperature times the natural log of something called the activity of that particular n-member species in a solid solution in a phase. Okay? Yes?
N prime?
N prime indicates that the activity of a particular species depends on the composition only of the phase that's n-member is in. That's what the prime is for. Okay? And so I've split this up intentionally because I'll spend some time talking about just this bit. How do you formulate the Gibbs free energy of the n-members of each of your phases, the pyrope, the forsterite, the phaolite, the enstatite, etc. And then I'll turn to looking at this compositionally dependent term afterwards. Okay, so let's focus on computing the Gibbs free energy of n-member phases. Okay, pick your favorite one. I don't know, I like to think of forsterite for some reason. So pick forsterite. Okay. How do we compute the Gibbs free energy of forsterite as a function of pressure and temperature over the relevant range? Okay. Here's the traditional way to do it. This traditional way is enshrined in classic textbooks that are listed here, but also going back earlier than that in physical chemistry textbooks, in the materials engineering literature, going much farther back even than this. So it's a very well-known approach. It's very standard. And what you do is you write this exact relationship between the Gibbs free energy, the entropy, for which I'll use S, the temperature, the volume, for which I'll use V, and the pressure. Okay? And the D represents differential. So a small change in G is related to a small change in T and a small change in P, like this. Okay? So that's exact. And you can integrate this. This is one way to integrate it. You say that the Gibbs free energy at pressure and temperature is related to the value at some reference pressure and temperature, say room conditions. Okay? And then some integral at 1 bar from the reference temperature up to the temperature of interest. Integrate the entropy over that. And then at high temperature, you integrate up in pressure from the reference pressure to the pressure of interest. Integrate the volume dP along that path. Okay? And again, one of the things that's nice about this, most applications in material science and engineering, in geology, tend to be at either 1 bar or at relatively low pressure. And so this integral is mostly about this term here. And the nice thing about this approach is that the entropy is often measured. Actually, you can measure it calorimetrically by looking at small changes in the energy of a sample as you heat it. It turns out you can work out the entropy from that, and you can integrate this very directly, almost directly from the experimental measurements themselves, almost. And this term tends to be small. Okay. But that's a problem for applications to the deep Earth. Yes?
The first integral, why you use P0 not P?
Because this is a particular integration path. And the reason that people generally use P0 here is that that's where all the experimental data are. They're all at 1 bar, right? All to first order. 99% of all measurements of all materials are at 1 bar. So that's why that's P0. That's the integration path that is most directly tied to experimental measurements and to most applications of materials properties as well. Okay. For applications to the deep Earth, though, this is problematic. And the reason for that, what I've done here is I've drawn out that integration path schematically here, temperature versus pressure. First, you go up in temperature at low pressure, right? You integrate that SdT. And then, up at high temperature, you integrate up in pressure. What I've also done here is indicate schematically where the melting temperature might be along this black line here. And I've also indicated a dashed line where materials, eventually, most solids become actually elastically unstable. Nasty things happen, like the bulk modulus vanishing or the shear modulus vanishing. And so above that dashed line, the Gibbs free energy is actually undefined. Okay. So if we're thinking about forsterite, say, or magnesium silicate perovskite for applications to the deep Earth, you want to go up to 100 GPa and 4,000 Kelvin, right, in principle? So going up at 1 bar to 4,000 Kelvin, you're going way above the melting curve. Okay, so you can't actually measure the properties of perovskite along most of this integration path because it's melted long ago and it's become elastically unstable, possibly. And you don't have data to constrain this part of the integration path either. Again, because perovskite isn't stable at those conditions, you can't measure it. So we need something else. And the way we formulated things, one way to develop it is like this. You can start from the first law, which relates, I'm introducing another energy here, and we'll have to get used to switching back and forth between different energies. This is the internal energy, and this is the standard statement of the first law that many of you will have seen. TdS, the heat, minus PdV, that's the work, and then plus a term related to changes in chemical composition. The crucial thing one of the crucial things we're going to do 2 crucial things, these 2 here. And the first thing that we're going to do is we're going to rewrite this expression, which is in this differential form. We're going to write it in absolute form, okay? Not differential, not du, but u itself. And the reason you can do that is because these thermodynamic potentials have a very special property, which is that they're first order homogeneous. And what that means, basically, is that if you double the entropy, double the volume, double the number of moles, then the energy doubles. Okay? So it's this nice relationship between scaling of the variables and scaling of the function itself. And it's because of that property that you can write the internal energy like this in terms of absolute quantities, not differential quantities, and that's crucial. The other thing that is important to us is that we can relate these different thermodynamic potentials or energies to each other through something called the Legendre transformation. And I'll illustrate this a bit in a few slides. So, for example, we can. Well, let me back up. One of the difficulties of this formulation here. This is a fundamental thermodynamic relation, so in principle, very good. One of the downsides of using this as a fundamental thermodynamic relation is that one of the variables is entropy. Now, entropy is not so easy to control in the laboratory. It's generally not controlled, right? You control the temperature, not the entropy. So we would like to have a fundamental thermodynamic relation that had temperature as the independent variable, not entropy. And here's how you do it. You Legendre transform it. U minus Ts turns out to be the Helmholtz free energy as a function now of temperature, volume, and composition. So, great, temperature. Chemical equilibrium is defined by the Gibbs free energy. Chemical equilibrium occurs at constant pressure. It's the pressure that's homogeneous across coexisting phases, not volume. So to do chemistry, we need the Gibbs free energy. And you can get that by Legendre transforming the Helmholtz free energy like this. Just add PV to it, and you get the Gibbs free energy. The other thing I'll mention as we go through this in a little bit more detail in the next few slides is this anisotropic generalization. If you want to apply this to seismology or any process that involves deviatoric stress, not just isotropic stress, then you need to generalize volume to strain and pressure to stress. Okay. So the Euler form is important because it allows us to calculate properties across the entire pressure temperature regime of the Earth. This is just an example calculation that I've done just to illustrate this idea, where I've calculated the Gibbs free energy of magnesium silicate perovskite. This is the Gibbs free energy of formation from the elements. And this is how the Gibbs free energy varies as pressure increases at 300 K. And here's how it changes at 4,000 K in the blue curve here. And one of the things, a couple of things I want to point out here. One is that unlike most applications of material science to engineering, to relatively low pressure metamorphic or igneous petrology, is that where the effect of temperature is completely dominant on the Gibbs free energy, if you're looking at the deep Earth, things are very different. Because here's the effect of temperature from 300 to 4,000 K, and here's the effect of pressure. So the effect of pressure is actually much greater if you're looking at the deep Earth than the effect of temperature. And so it's important to get that part right, that the volume dependence or the pressure dependence of the free energy right. And that's one reason why the Euler form is so valuable. The Legendre transformation, this allows us to relate the Gibbs free energy, which is going to give us chemistry, to the Helmholtz free energy, which is a function of volume. Why is that important? Because most theories of material behavior tend to think of volume as the independent variable, not the pressure. Why is that? It's not because theorists are perverse. It's because they tend to think in terms of fixing the geometry first and then going from there. And fixing the volume fixes the geometry of the system, and then you can start examining the physics. So we need to be able to go back and forth between these two, and luckily it's very easy to do. You just add PV. This is a graphical way of looking at it. Plot Gibbs free energy versus pressure. Here's in the blue curve here, okay? And you can equally well describe this curve as the family of tangents to it. Here's an example of one tangent to the curve at a particular pressure. And the intercept then is the Helmholtz free energy at that point, and the slope is the volume, okay? The things that relate G and F to each other. Okay, let me ask the seismologists in the room. We've got this curve here, and we've got tangents to it, a family of tangents to it. Does that remind you of anything? Tau P. Tau P analysis of travel time curves, right? It's the same basic idea. Okay.
They can both have triplications.
So, yeah, unlike this. Yeah, okay.
A triplication in here is a critical point.
Yeah, or a Wouldn't it be a first order phase transformation? Because at the triplication, you have a sudden change in slope. So
right,
it would be a sudden change in volume, so first order phase transformation.
Where a first order phase transition goes away at a critical point is the same as where two different branches of a seismic ray converge at a caustic.
Right. Yep. Yes. Same slope. Yeah. Okay. So one of the things about thermodynamics is that there are lots of variables. That's its power, is that you can its scope is so great that you can encompass a huge number of different material properties, but sometimes it is a bit difficult to keep them all straight. So people who do thermodynamics think of various mnemonic devices to try to keep them straight in their head. And so, for example, this is a Thermodynamic Square due to Maxwell, the same guy of the electromagnetic equations. And what we have is that it relates the various thermodynamic potentials. I've mentioned 3 of these already: Helmholtz free energy, Gibbs free energy, internal energy, and here's another one, the enthalpy, to their natural variables. And so you write the thermodynamic potentials in alphabetical order, F, G, H, U. You surround them by their natural variables, P and T in the case of Gibbs free energy, V and T in the case of Helmholtz free energy, V and S in the case of the internal energy. And then you draw these 2 arrows. And with this square, you can do a couple of fun things. One is that you can figure out the first derivatives of the thermodynamic potential. So, for example, dg dp is equal to the opposite corner, V. All right? dg dt is related to the opposite corner, entropy. If you go to the opposite corner along the arrow, you get a positive sign. So dg dp is plus V. If you go against the arrow, you get a negative sign. dg dt is actually minus S. And df dv is minus P, df dt is minus T, etc. The other fun thing you can do, which is even more amazing, I think, is you can do Maxwell relations. So second derivatives of the thermodynamic potentials. Okay. Yeah. You can do that. So how do I raise this? Is that going up?
There's a light that you can.
Okay. Good. Okay. Yes, B. Yes. Good. Okay. F, G, H, U, T, P, V, S. 2 arrows. First derivatives, for example, dg dp is equal to V, dg dp, and we're taking this derivative at constant, the other natural variable. Okay, you have to be careful in thermodynamics. You always have to write derivatives specifying which quantity is being kept constant while you're taking the derivative. And that's how you write that, keeping temperature constant. dg dp at constant temperature is equal to V, and that's this. That's this path here, okay? And dg dt at P is equal to minus S, and that's this path here. dg dt is equal to minus S. And it's a minus sign because you're going against the arrow. All right. The other thing you can do is second derivatives. You can relate second derivatives to each other. Okay. The basic idea is very simple, but then it ends up looking quite rich. The basic idea is just this. Okay, the Maxwell relations are all of this type. Taking a second derivative, it doesn't matter which order you take the derivatives, right? And so, for example, one of the more remarkable ones, I think, and useful, I'll mention it later. Let me do this in green. The SDP at T, okay, so ds dp at constant temperature, ds dp at constant temperature, is equal to, start at the unused corner and go in the opposite direction, dv dt at constant p. Whoops, wrong color.
Minus sign.
And yes, I was going to get to that. And is there a minus sign? The way you tell whether there's a minus sign or not is you look at the two corners. Do the two corners have the same end of the arrow? Well, the first corner has an arrow tail, and the second corner has an arrow head. So that's a minus sign. Okay, and so this is really cool. This is the thermal expansivity here. All right, the thermal expansivity turns out to be related to how the entropy depends on pressure. Wild, but it's just this. It's literally just this. Okay, let's go back. Okay, good. Okay, Thermodynamic Square. Not a comment on the personalities of thermodynamicists. Right? Okay. This is another way to summarize the various properties that we're dealing with. We can think of constructing a matrix where where you have operators along the top and along the side. The identity operator here. Take the pressure derivative, the temperature derivative, and down this side as well, and operate on the Gibbs free energy is what I've chosen to do in this case. Two identity operators on G just gives you G back. Taking a pressure derivative gives you V. Taking a temperature derivative gives you minus S. And the same along here. Second derivatives are more interesting. Take two pressure derivatives, you get the bulk modulus. That pops out. Take two temperature derivatives, you get the heat capacity. Take the mixed derivative, pressure then temperature or temperature then pressure, you get the Maxwell relationship that I just wrote on the board there. Okay, so sort of a reminder of some of the properties that we're interested in, some mnemonic devices for remembering some of them. And I think the point is that thermodynamics can look like a zoo of completely unrelated quantities. But of course, they're not. They all are related to each other. And that's one of the beautiful things about it. OK, now the next question is, how we need some kind of functional form. We need some way to represent our fundamental thermodynamic relation. We need to actually get specific now and specify it. How is the Gibbs free energy going to depend on pressure and temperature? Or how is the Helmholtz free energy going to depend on volume and temperature? What is the functional form actually going to be? If we were interested in ideal gases, the answer would be very simple. You can write it down on the back of an envelope. But unfortunately, for most planetary materials, including the gases in giant planets, which are not ideal gases at all because they're at such high pressure, the ideal gas law just doesn't work. And one of the reasons for that is that the interaction between the atoms is important. It matters. In an ideal gas, it doesn't. But in planetary materials, it does, very much so. And the interaction between atoms is complicated because you have to think about the electron clouds or shells, and you have to think about their overlap, and you have to think about how their overlap deforms the electron cloud. So it's a very complicated problem. For some bits of this fundamental thermodynamic relation, there are fairly straightforward answers to what the functional dependence should be. For other parts, there aren't. Here's one part where there isn't a straightforward, that's obviously the functional form. Okay, we just don't have that for this part of the fundamental thermodynamic relation. So here's what we're after. We want to specify this functional form here. Helmholtz free energy is a function of volume, temperature, and composition. And we're just focusing on constant composition for the moment, just n members, right? And let's just look at, to keep it simple, let's first focus on just how it depends on volume, okay? So let's break it down to the simplest possible form. How does this thing depend on volume? We don't know. There's no way to derive this. There's no simple way to figure this out. You can do ab initio theory. You can calculate this from first principles. You can measure it. But the first principles theory or the experiment won't uniquely give you a functional form. But we have to do something. And so what we do is what physicists generally do in cases like this, is that you punt. And you say, let's make a Taylor series expansion. Okay. This doesn't have any physical content. Okay. It doesn't have to be a Taylor series expansion. Except that the expansion variable has to be volume. Okay, that's a requirement of the fundamental thermodynamic relation. It has to be volume or function of volume. Has to be that. What are we going to choose? Well, one possible choice is the Eulerian finite strain. And here is the isotropic part of it, written here. Wendy also showed this yesterday. That's one possible choice. Let's see what happens if we make that choice. Okay, let's expand the Helmholtz free energy in a Taylor series in little f, the Eulerian finite strain. Right? I've left out the linear term because I'm assuming that the reference state is zero pressure, and I've left out the constant term because we'll talk about phase equilibria later. Here we're just interested in the properties of n members. How can we evaluate this choice? One way to evaluate it is to examine the radius of convergence of this Taylor series expansion. If we just cut it off at the first term, how well are we doing? Right? Well, you can work out by taking volume derivatives of f what A is related to in terms of physical properties of the material. And here's the relationship here. A is given by 9 times the bulk modulus at zero pressure times the volume at zero pressure. Now, these two are independently measured. I know the volume of magnesium silicate perovskite at zero pressure. I know the bulk modulus from Brion spectroscopy. And if I plug those values in and calculate how F depends on finite strain, I get this curve here. And I can compare that now to independent experimental measurements, where people using the diamond cell have actually measured pressure and volume, and those points are here. And so this is the reason why we use Eulerian finite strain, because it works. There's nothing that tells us that that's the best choice or the unique choice. It's certainly not the unique choice, but it does happen to work. You can make arguments about what's good about it in the sense that this second-order coefficient tends to be quite small because K prime, that we heard about yesterday, tends to be close to 4, and that is a result, a consequence of choosing Eulerian finite strain, that this coefficient here goes like K prime minus 4, so it tends to be quite small. If you choose a different finite strain, and there are many different finite strains you could choose, and I'll look at another choice a little later, you'll get a very different relationship between for
Just
K prime.
to be clear in this case, before you go on, is that curve fitted to the high pressure data or predicted from ambient pressure measurements?
It is predicted from ambient pressure measurements. It is not fit to the high pressure data. And that's why this is so nice. It's a really nice demonstration of how fast this Taylor series expansion converges. Okay. Yes.
Sorry. If it's predicted from low pressure, how'd the coefficient 9 come up?
Oh, that just comes out of what I've done here. What I'm doing here is I'm taking 2 volume derivatives of the Helmholtz free energy, and you can see that that's going to be a little bit messy because of the relationship between little f and volume, and so that's where factors like 9 end up coming from taking those 2 derivatives. Yeah. Okay, so that's the cold part, a Taylor series expansion in the Eulerian finite strain. What about the thermal part? Let me back up and tell sort of a geophysics story now, having to do with the thermal part. and having to do with the origin of the low velocity zone. In the very early days of mineral physics, people were interested in the origin of the low velocity zone. They realized the temperature would be involved somehow. And so what they did is they took the minerals that they thought were abundant in the low velocity zone and measured how their seismic wave velocities depended on temperature in the laboratory. Okay? People like Orson Anderson, for example, at UCLA did this. The temperature range that was available to them in those pioneering days was quite small. In fact, just literally a few degrees centigrade. But he had very precise measurements, which he might have made, I've always wondered about this, just by heating up the room, turning up the thermostat. But anyway, he got a pretty good measurement of the temperature derivative of the seismic wave velocities at sort of room temperature. And applying that then, using those temperature derivatives, applying them to the origin of the low velocity zone, they got these curves here, okay, along what they thought was a reasonable mantle geotherm, okay, with a sort of conductive thermal boundary layer and an adiabat down here. And they got these enormously high velocities, much, much higher than seen by seismology. And they said, aha, the low velocity zone must have partial melt. The weakness in that is that the temperature derivative depends on temperature. And it has to. And this is one way to see it. It's required by the third law that the temperature derivative has to depend on temperature. Okay? If you look at 0 Kelvin, for example, at 0 Kelvin, temperature derivatives have to vanish. Here's this Maxwell relationship that we saw before, relating the pressure dependence of the entropy to the temperature dependence of, in this case, the volume, which is equal to thermal expansivity times volume. All right? Now, the entropy at 0 Kelvin is 0, right? And so its pressure derivative is 0. And that means the thermal expansivity has to be 0 at 0 temperature. It's a requirement of the third law of thermodynamics. And so if you plot shear wave velocity versus temperature, the derivative starts out at 0. At room temperature, it's bigger than 0, but at sort of mantle conditions, it keeps getting bigger and bigger. So if you take temperature derivatives near room temperature, you'll get the wrong idea about what high temperature velocities should be. And we've put some physics in, and other people have done this, looking at the origin of the low velocity zone. Taking into account this effect, you get much lower velocities, and the question of partial melt in the low velocity zone is still up in the air, I would say. Okay, so we need some physics. Obviously, we need to put some physics into the thermal part, and this is one part of the fundamental thermodynamic relation where we can put in some physics. And so let's look at what temperature is doing to the material. What it does is it causes the atoms to vibrate. And this is one way of looking at those vibrations. What I'm doing here is plotting the energy of the crystal as a function of interatomic distance. Okay? So let's say we're looking at a very simple material that just has one interatomic distance, like MgO or something like that. And it has some favorite bond length here, 2 in whatever units I've chosen here. If you compress it, the energy rises. And if you stretch it, the energy rises because the bond length is now unfavorable. Compression and expansion are asymmetric. They don't do the same thing because as you compress the material, the electron clouds start to overlap and the energy rises very quickly. As you stretch it, though, the energy rises more slowly because in the limit that you've separated the atoms an infinite amount, the binding energy just trails off, asymptotes to 0. It doesn't go off to infinity, it asymptotes to 0. And so we get this asymmetric dependence of energy on distance. This is called an anharmonic well because of this asymmetry. Now, what if we try to approximate this anharmonic well? This is a messy function to work with. Maybe we can do something simpler. Let's approximate it by a harmonic potential, which is given in red here. And this harmonic potential has the same curvature as the full anharmonic energy versus distance curve near the origin. And one of the motivations for doing this is that the temperatures that we're interested in geophysics tend to be fairly small compared to binding energies of materials. So we're generally interested in a range of thermal energies exciting lattice vibrations that are down in this range here, where the red and green curves are fairly similar to each other. And so this is the harmonic approximation to lattice vibrations, and you can imagine the bonds in a particular material stretching and compressing, stretching and compressing in response to thermal excitation, and following more or less this harmonic potential well here. Now, one of the downsides of this harmonic approximation to the true energy versus distance curve is that it predicts that there's no thermal expansion at all. Okay? Thermal expansion is 0. So that's obviously a problem. So maybe we need to go back to the anharmonic potential after all. Well, actually you don't. You can do something else. And this is what's called the quasi-harmonic approximation. And in the quasi-harmonic approximation, what you do is you say, here's our approximation to the energy versus distance curve at low pressure, and here is our approximation to it at higher pressure. What we've done is we've compressed the material. The minimum energy distance is now smaller, and the curve is now sharper. It's sharpened up, and what that corresponds to, a higher force constant, higher vibrational frequency, is that the vibrational frequencies increase on compression. Bonds get stronger, the atoms start vibrating faster against each other. And so what's happening is that the frequency of the material is changing with compression. Low frequency at low pressure, high frequency at high pressure. And one way to describe that change in frequency with volume is in terms of something called the Grüneisen parameter. In this way here. It happens to be minus the logarithmic volume derivative of theta, which is the characteristic vibrational frequency. Now, it turns out that in the quasi-harmonic approximation, if this is going on, if the crystal is always harmonic, but you allow the frequencies to change with compression, that's the quasi-harmonic approximation, in that approximation, then this is exactly equal to the thermodynamic definition of the Grüneisen parameter, V times the change in pressure with internal energy at constant volume. And it turns out to be important how Grüneisen parameter varies with volume as well, and you can describe that with a further logarithmic volume derivative, which gets the name Q. Okay, here's another way to look at all that. Here's an equation of state. Wendy showed a similar curve yesterday, set of curves yesterday, pressure versus volume. A cold equation of state, say 300 Kelvin, and a hot equation of state, say a mantle temperature, 1500, 2000 Kelvin, something like that. As Wendy pointed out this way, there are two ways to think about the relationship between these two curves. One is in terms of thermal expansion, which is changing the volume at constant pressure, right? You heat and the volume expands, right? Another way to think about it, because theorists like to think in terms of volume being the independent variable, volume being constant, hold the volume constant, what happens? The pressure grows as you heat, and that's called thermal pressure. We can think about Grüneisen parameter and how it depends on volume by comparing these two curves. It turns out that the thermal pressure is pretty nearly equal to this, where this is 3, this is the number of atoms in the formula unit, ideal gas constant temperature, and there's the volume again, and multiplied by the Grüneisen parameter. So the Grüneisen parameter dictates the magnitude of the thermal pressure. Now, if you look at these curves, the thermal pressure is big over here at low pressure, but as you go up in pressure, they get closer and closer together. And this is very typical of crystals. Thermal effects tend to be squeezed out. That's often how we think about it. And so the thermal pressure shrinks as you compress. For the thermal pressure to shrink on compression, gamma has to decrease on compression. And because of the 1 over V, it has to decrease faster than the volume, actually. And so that tells us something about Q. It tells us, in fact, that Q is generally greater than 1 for crystals. about 1.5, 2, something like that. Some of them have much larger values, a few of them. Q is defined to be this, the logarithmic volume derivative of gamma. That's the definition of it, yeah. So Q has to be greater than 1. And how can we constrain this? Now, a common assumption is just to assume that Q is constant, okay? And in the early days of shockwave experiments, Q being constant turned out to be good enough to match with a lot of the shockwave data. And so that has become sort of enshrined in the geophysics literature as a common assumption. If you do ab initio theory, though, and there's some experimental data to back this up as well, what you find is that Q, in fact, is not constant. And this is an example of ab initio calculations. This is on magnesium silicate perovskite, where I've plotted, oh, sorry, I've left off this. This is volume going from 1 to about a half of the zero pressure volume. And this is Grüneisen parameter as the symbols here, and I'm also plotting Q. So the symbols are the results of ab initio calculations, and what's shown in blue here is what you get if you assume that Q is constant. Okay, so the dashed lines are Q. So if Q is constant, then the Grüneisen parameter whoosh decreases very rapidly on compression, much more rapidly than the ab initio theory indicates. And so this is an example of how we can use ab initio theory to put constraints on the functional form of the fundamental thermodynamic relation. Instead, we have a different theory for how Grüneisen parameter depends on compression. All we do is we expand. We use the Taylor series expansion again. We expand the characteristic vibrational frequency as a Taylor series in the Eulerian finite strain. And with that, we get this curve for the Grüneisen parameter and this curve for Q. So Q is actually decreasing on compression.
Lars?
Yes?
So that you've got the Q is dropped below 1 at low volume, so high pressure. So that means at very high pressures, you actually get increasing thermal pressure? Or?
Yeah, that's right. Which is interesting. That's what comes out of the ab initio theory. Yeah.
The limit at extreme compression is gamma goes to 2/3 and stays constant. So under those conditions, yes.
That's right. Yeah. So, yeah, there are these infinite pressure limits to a lot of the thermodynamic quantities, and people like Frank Stacey have written papers about them. I think one has to be a little bit cautious about the infinite pressure limits because a lot of them apply to something called a free electron gas. So as you go up in pressure, the electrons become more and more delocalized. They become less tied to individual nuclei. And so you end up getting this jellium, this uniform background of electrons in which the nuclei are embedded. And that limit is also one that you can write on the back of an envelope. You can calculate all the properties of that jellium model very easily. The reason I say I tend to be cautious about applying that infinite pressure limit is that I think even in the center of the Earth, you're very far away from that infinite pressure limit. There's still lots of phase transitions to go, lots of changes in structure before you get to that infinite pressure limit. Yes?
I just wanted to see if I'm correct in thinking. When you started talking about this infinite pressure limit, I started thinking of the work of Bukowinski and many others that actually looked at how alkali metals change to transition-like metals. So is it along the same lines of what's happening to the electron state?
It's along the same lines, yes. So if you look at potassium, Mark Bukowinski looked at potassium, which is an alkali metal at low pressure, but as you compress it, the D states end up rising in energy less fast than the S states, and so potassium becomes a transition metal as you go up in pressure. And that's just one example. I'll show you a few more of changes in the electronic structure that can happen on the way towards this infinite pressure limit. Lots of interesting things can happen, and the Grüneisen parameter can go up and down and up and down. It doesn't necessarily smoothly tend towards this 2/3 infinite pressure limit. The other thing that we've done is this anisotropic generalization. So writing the Helmholtz free energy not as a function of volume, but of strain, actually. Again, we've chosen the Eulerian finite strain. Again, demonstrating self-consistency. For example, the elastic constant tensor, which is a fourth-rank tensor, you can relate to the second strain derivative of the Helmholtz free energy in this way. It turns out there's this extra term here, where these are Kronecker delta functions, which are 1 if I and j are equal, 0 otherwise. And you can demonstrate self-consistency like this. This relationship is true for any material, regardless of the symmetry of the elastic constant tensor. And then, of course, the bulk modulus is related to the volume derivative of the pressure, which is related to the second volume derivative of the free energy. So you can go back and forth from free energy to elastic constants. Okay, back to this business of the choice of the strain tensor. So we've chosen Eulerian finite strain. I tried to motivate that. I'll motivate it a little more in the next slide by comparing to a different choice of finite strain tensor. It turns out there's an infinite choice of finite strain tensors. The infinitesimal, the Cauchy, is unique. But finite strain, there's an infinite variety of choices. And one way to think about the difference between Eulerian finite strain versus Lagrangian finite strain is to think about the following problem. I give you two lengths, a length of 8 and a length of 9, and I ask you, what is the fractional change in length? Is it 1/8 or is it 1/9? And that's one way to think about the difference between Eulerian finite strain, which uses the final state as the reference state, and Lagrangian finite strain, which uses the initial state as the reference state to the strain. So let's see what the consequence of those two choices are. Here I'm plotting elastic modulus versus pressure. This is from magnesium silicate perovskite. The symbols are ab initio calculations. They turn out to agree perfectly with the subsequent measurements of Murakami et al. And the red is the Eulerian finite strain result, truncated at third order. Where I've just used the initial value of the bulk modulus and its initial slope to calculate this curve. And again, for the shear modulus, the initial value of the shear modulus and its initial slope. And you get this very nice agreement between Eulerian finite strain and the ab initio results and the subsequent experimental results. What about Lagrangian strain? What if I chose Lagrangian strain instead? Using exactly the same values of the initial elastic modulus and its initial pressure derivative, this is what Lagrangian finite strain tells you. It tells you that the shear modulus goes off like this and the bulk modulus goes off like that. Total disaster, right? So Eulerian finite strain is a lot better than Lagrangian finite strain, and it turns out to matter which finite strain you choose. Eulerian finite strain, as far as we can tell, is the best choice in the sense of agreeing with what real materials do.
Lars, is there a simple explanation why?
No. No, there's no simple explanation why.
The Lagrangian strain tend towards half for infinite compression, though?
There are funny limits at infinite compression, no matter which finite strain tensor you choose. You can also choose this logarithmic strain, which also doesn't do nearly as well as the Eulerian. I think it tends to be in between these two, sort of halfway in between these two.
Yeah.
Yep.
Lars, it seems somehow that we have information about the end state by using the Eulerian.
Maybe that's why it works better. Yeah, it's not obvious to me. You can and people have tried to think about the geometry of that, about the reference frame, about using the final state as the reference state. Maybe that has some significance to it, but it's certainly not obvious to me.
When Birch did this, he used Eulerian.
He used Eulerian, yes.
So how much of this did he understand, or was it just good scientists make good choices?
Yeah. If he had chosen Lagrangian, we wouldn't remember his papers, right? Yeah.
Just to clarify, this is the difference between the two approaches when you truncate it at the first term. Is that right? And if you take it
this is third order. So in both cases, I'm using two terms, the first two terms. Yeah.
Okay. But if you were to take it to further terms, then presumably the Lagrangian would also work.
You can make any Taylor series expansion work by including more terms, right? And the key is the radius of convergence. You want to have as small a number of terms in your Taylor series expansion as possible, because that makes your model more robust. It means that you have to constrain fewer parameters to specify the physical properties.
And the picture and your conclusion won't change if you compare with decompression data in experiments, right?
Well, if the experiment is well constrained, if there aren't other funny things going on in the experiment, these kinds of data should be reversible. The bulk modulus should be the same going up in pressure as it is coming down. If that's not the case, then there are additional variables in the experiment that aren't included in this analysis, such as dV torque stress, or I don't know. Bulk viscosity. Yeah, bulk viscosity, we assume that time scales of expansion and compression is not a serious issue, that it's sufficiently rapid. Yeah. And there's no evidence to the contrary, at least in room temperature experiments.
I'm just a bit curious.
Yeah, non-equilibrium phases like glasses, they compress irreversibly. Yeah.
So on this plot here, I mean, I have nothing about Lagrangian or Eulerian. I mean, I like them equally. I don't care. Mm-hmm. But we choose one because it's closer to the dots. But the dots are ab initio calculations, which you told us are not perfect. I mean, there could be an error. How do we know they're right here?
Okay, we don't. But this is one way we try to address that question. Is that Okay, here are the same dots that I was just showing you, the red dots there. We published these in 1997. And the red is the same Eulerian finite strain match to those that I just showed you from our 2005 paper. The squares are subsequent measurements by Murakami et al. So we're pretty happy with that. Absolutely. Okay, let's see. How are we doing? All right. Temperature dependence of the elastic constants. This again, this comes straight from the assumptions I've told you about already. Expand the Helmholtz free energy as a Taylor series now in the elements of the finite strain tensor, the full tensor, right? Expand the characteristic vibrational frequency as a Taylor series in the isotropic part of that. Take strain derivatives, and this is what pops out. And here you see this is a finite strain expansion. There's F squared. The coefficients end up depending on the pressure derivative of the elastic constant and also the bulk modulus and the elastic constant itself. There's the pressure derivative again of the elastic constant. There's K prime, etc. So this is just what pops out. And the temperature dependence ends up looking like this. This is the Gruneisen tensor. So I showed you before that for isotropic materials, gamma is V times dP du. For anisotropic materials, which is all crystals, it's d sigma ij du. So it's a tensor actually, and this is the strain derivative of the Gruneisen tensor here. And what we've assumed is that the Gruneisen tensor and this guy, its strain derivative, are isotropic. Okay, and that's an assumption that needs further exploration. There's not a large amount of data that's able to test that approximation. The data that's the best data that we found that's available, the approximation turns out to work pretty well. But there's certainly room for improvement there. Okay, so this is our fundamental relation. We have a cold part, which we talked about. We have a thermal part, which we talked about. These are the parameters. Zero pressure volume, elastic moduli, their pressure derivatives, characteristic frequency, its volume dependence, the volume dependence of gamma, This is the, we're assuming that eta tensor is isotropic, so this is the shear part of that isotropic fourth rank tensor and a reference free energy. And a couple of additional terms for oddball phases like quartz, which have this weird second order transition from alpha to beta. Okay, so what can we do with this? What can we do with Hephaestus? We formulated this. What can we do with it? The basic idea, again, just to take a step back, what we're trying to do is we're trying to gather all this experimental data and trying to express it in the parametrically simplest possible form, which has as much physics built into it as possible. Things like the variation of the composition of garnets and whole rock compositions, sort of one component phase equilibria here, variation of elastic moduli with temperature, variations in phase proportions in whole rock compositions, thermochemical properties like the heat capacity, and variations in elastic moduli with pressure. And again, the idea is that all of this comes from a single function that gives free energy as a function of stress, temperature, and composition, or equivalently Helmholtz free energy as a function of strain, temperature, and composition. Here are all the parameters. I don't expect you to get a lot out of this. So, but there is a code that inverts all that data and produces the best guesses at all the parameters, and actually spits out a LaTeX file with all the references as well. There are like up to 140 references now to this experimental data. And in red, I guess one interesting point, these are the various species that we've included in Hephaestus so far. And in red are those for which there is no experimental constraint, or at least as of 2011, we couldn't find any experimental constraints or ab initio constraints on these properties. So some of these we still have to estimate. Yes?
How often do you update these parameters as new experimental data comes out?
As often as possible. Okay. But there is good stuff coming out all the time, and I do my best to try to keep up with it. Yeah. But there are some things that we just need to know better. Obviously, you see, there's not a whole lot of red on this table, but there is some. At least for the most abundant N member of all the mantle phases, I think it's fair to say that we know all the parameters of at least the most abundant one.
Lars,
yes?
This is the 2011, right? This is not the latest.
This is the 2011 version, yes. Yes, we've updated it since then. Yeah. Yeah.
Does it propagate uncertainties in each of these parameters through to the final?
Yes. Yes. Yeah, so we have tried to estimate uncertainties based on changes in the global chi-squared fit to the experimental data, and the uncertainties are given here as well. One thing to be careful of is that some of the errors are correlated with each other. So K and K prime are it's very well known that there is correlation in those. So if you increase K and decrease K prime, you can get a very similar fit to pressure volume data. So there are correlations. We haven't done a super fancy Monte Carlo inversion of the uncertainties. We've tried to keep the estimates of uncertainties as simple as possible. Okay. One thing that I think it's easy to lose sight of in discussions of uncertainties and constraints and so on is that one of the exciting things about mineral physics is that you discover new stuff all the time. And let me give you a few examples of that, of things that we've just included in Hephaestus or we haven't gotten around to including yet, but which probably are quite important either to the Earth or to other planets. This is one example that we're just getting around to including now. This is anharmonicity in magnesium silicate perovskite. If you remember, I argued that the quasi-harmonic approximation was pretty good for geophysical applications, and that's true. But if you're interested in very high temperatures, anharmonicity can start to matter. And this is an example of where it actually matters. This is magnesium silicate perovskite, we did some molecular dynamics simulations of this material. And what's represented here are the Si6 octahedra that make up this structure, and in the middle, the magnesium sitting in this big site. And this golden knot here is the path that the magnesium atom takes during the course of this simulation. Very large amplitude, very complicated, quite anharmonic. And you can demonstrate anharmonicity in various other ways as well. This is what we assumed in Stixrude and Lithgow-Bertoloni 2011. We were tying ourselves to lattice dynamics calculations, which assume quasi-harmonicity. They're ab initio, but statistical mechanically, they assume quasi-harmonicity. So we were tying ourselves to that and getting this for the temperature derivative of the shear modulus. Instead, the molecular dynamics simulations show a much gentler dependence of the shear modulus on temperature. And the difference here is not the ab initio theory per se, it's approximations in the statistical mechanics. This calculation assumed quasi-harmonicity. These calculations don't make that assumption. They're more expensive, they're harder, but in this case it was well worth doing. And you get a much gentler dependence, which then has implications for understanding the composition of the lower mantle. Another example of sort of new behavior that we're just starting to incorporate. Remember I told you how the Gruneisen parameter decreases on compression. And it does for all crystalline phases, but not for liquids, it turns out. This is a result of ab initio calculations, prediction of ours, which was then confirmed experimentally by Paul Asimov and co-workers, where we calculated the Gruneisen parameter based on molecular dynamics simulations of silicate liquids. This is volume here in some units, and you see the Gruneisen parameter increasing very rapidly. Increases by a factor of 3 on twofold compression, increasing very rapidly with compression. And that has really interesting implications for the magma ocean. Makes it hotter at depth, much easier to melt the Earth, and so on. Another example is high-spin, low-spin transitions. We haven't included these in Hephaestus yet, partly because they're not that well understood, I feel, especially for perovskite. It's a bit of a mess in terms of intermediate spin and different sites, different valence states. For ferropericlase, it might be worth including it at this point. This is what it looks like in melts. This is a Fayet composition melt, and this is the local magnetic moment on average on the iron atoms in this melt, and it decreases with compression. We're going up to almost 300 GPa here, and this is our best estimate, our best guess here, and it's decreasing very, very slowly. So the high-spin, low-spin transition looks really different in silicate liquids as compared to crystals. I couldn't resist this one based on the very interesting research talk we heard yesterday afternoon about Saturn and its interior structure. If you remember, he didn't have rocky core and then hydrogen-helium envelope with a sharp boundary. He had sort of a gradual boundary between rocky core and hydrogen-helium envelope. And this is one reason to think that might actually happen in Saturn. These are calculations from Burkhard Militzer and others. And what he's done is he's estimated how much silica, as sort of a model of rock, how much silica can you dissolve in hydrogen? And this is temperature versus pressure. Here's the core mantle boundary in Jupiter, the core mantle boundary in Saturn. And what he's saying is that you can dissolve silica in hydrogen in the amount of 1 to 100. And if you think about how big the core is compared to the mass of the whole planet, that's quite a lot. That's a lot of the core that you can dissolve in the hydrogen envelope of Saturn. And so that sort of gradual transition between rocky core and hydrogen-rich envelope actually has some basis in these ab initio calculations.
Lars, before you move on, can you comment on something? So you said silica as a model for a rock, but has added iron or something else. Does that change the solubility?
Yeah, so iron turns out to be even more soluble than silica, native iron.
But if silica prefers being with iron, right, to make perovskite or something else?
Yeah, could change things. Absolutely. It could change things. They've started to address that by also looking at MgO here, and you see MgO is less soluble in hydrogen at more or less the same temperature, only 1 to 1,000. Yeah. So there's a lot more to do on this, obviously. Okay, let me go back to the dependence of the free energy on composition. Haven't said anything about that yet. I'm not sure how much of this I should do. Basically, we assume not quite ideal solutions, but we make the simplest correction to ideal solutions. So what's an ideal solution, first of all? Here's the crystal structure of olivine. You have these octahedral sites where the magnesiums and irons can go. What you do, because the magnesiums and irons don't interact very strongly with each other, is you count all the different ways you can arrange the magnesiums and the irons over the available sites. And then you use the Boltzmann formula to figure out the additional contribution to the entropy due to that magnesium-iron disorder. And the entropy ends up depending nonlinearly on composition. And so if you look at the Gibbs free energy of a phase as a function of composition, say for Forster here, for example, it ends up having this curvy shape to it. And that's because of this entropy of mixing, right? It's favorable to mix end members. They want to mix because there's this additional contribution to the entropy. So the free energy of Forster might look like this. The free energy of Wadsleite, the high pressure phase, might look like this at relatively low pressure. And since the Gibbs free energy of alpha is lowest everywhere, that means that alpha is the stable phase everywhere in this phase diagram. At high pressure, they reverse. The beta phase is now stable everywhere, lowest Gibbs free energy compared to alpha, and so you get this pure beta stability field. In between, they cross. And this crossing is really interesting. You can figure out the compositions of the coexisting phases by this common tangent construction here. The composition of alpha is given by that point, composition of beta by that point, and that gives you 2 points on this banana loop, this two-component phase diagram here. We include the first-order correction to ideal solutions by including energetic effects. The magnesiums and irons do interact a little bit, and so it matters whether you arrange them like this versus this. And there's a simple way to incorporate that. And this is just one example of the diopside calcium Chermak solid solution and some experimental data here and our fit to that experimental data.
The errors on calorimetry data, you can see that the enthalpy of solution is positive, but that's like almost all.
Yes.
So the optimization of these data to phase equilibria are a necessary step in the production of useful databases. It's
Absolutely.
Just a great plot for showing that.
Absolutely. That's absolutely right. And here's another example of what Paul was just saying. So what we're doing here is we're taking experimental measurements of phase equilibria in the Mg2Si4 system. Open circles are observations of Forsterite being stable. Closed circles where Wadsleite is stable. These open squares where Ringwoodite is stable, and so on. And we're inverting these for the reference free energies of the phases and for their characteristic vibrational frequencies. Okay? In the case of Forsterite, we know what the characteristic vibrational frequency is because we have thermochemical data at low pressure. But for Wadsleite, we don't, and for Ringwoodite, we don't, or at least not over a very large temperature range. And this just shows the solid lines show our best fit solution to these data, and the dashed lines show what happens if you change the reference free energy of Wadsleite by, I think it was 1 kilojoule per mole. You make it more stable by, or 1 or a few kilojoules per mole, I can't remember now. Make it more stable. That'll expand the Wadsleite stability field out to these dashed lines, right? And so this gives you an idea of the uncertainty in that reference free energy. What I've done here is I've increased the characteristic vibrational frequency of Wadsleite by 10%. And what that's done is that it's narrowed the Wadsleite stability field tremendously. It's also changed the Clapeyron slopes because the frequency is related to the entropy, so that changes the slopes. And so this tells you that you can constrain the vibrational frequency to much better than 10%. No, sorry, 1%. I changed it by 7 Kelvin out of 700 Kelvin. That's 1%, right? You can constrain it to better than 1%. And here you can constrain the reference free energy to better than a few kilojoules per mole. Okay, back to our central problem. Remember our rock. And what do we need to do? We need to find the stable phase assemblage, their compositions, the physical properties, all that stuff. Minimize the Gibbs free energy at a given temperature and pressure as a function of the amounts of all the species, the pyrope and the forsterite and the diopside and all that. Subject to constant bulk composition. Here's our n vector again. This is the stoichiometric coefficient matrix, which relates the amount of a species to the amount of each of the components in the system, MgO, FeO, SiO2, etc. And that you're not allowed to have negative amounts of any component on any site in the crystal. That's what this says. And these are the relationships among those various quantities. I wanted to mention this because it connects back to Mark Panning's talk yesterday. This is the essential problem that we have. This is the stoichiometric coefficient matrix. This is what we want to find, the amounts of all the species. This is our bulk composition. Now, the number of species in Hephaestus right now is 47. The number of components in a bulk chemical composition, the ones that really matter, are like 6 in the mantle, right? So that's 47. That's 6. This is an underdetermined problem in this form. And that means that there are many different n vectors that will satisfy this relationship, and so we need more to solve this problem. And what we need is to minimize the Gibbs free energy. We find the solution vector that satisfies this equation, but which also minimizes the Gibbs free energy. And one of the things you need to do, one of the things that's tricky about this problem is that it's nonlinear. It's inherently nonlinear because the Gibbs free energy depends nonlinearly on composition through the logarithmic term. And so you have to be very careful about which phases you're including. And we look at criteria like the chemical affinity for either adding or subtracting a phase from the solution. And in the end, you get something like this. And this is an example of the sort of thing that you can get. These are plots of phase proportions shown in the colors and seismic wave velocity of the assemblage as a function of depth. In this case, I've plotted it along a self-consistently computed mantle isentrope. And so for pyrolite, which is this phase equilibrium here, we get the green curve. No, sorry, the dash curve, the dash green curve. And you can see olivine, wadzlite, ringwoodite, those polymorphs. You can see the pyroxenes dissolving into garnet. You can see calcium perovskite exsolving out of the garnet there. Lower mantle dominated by perovskite and ferropericlase, and there's the post-perovskite transition there. And so you can you can explore this, and this is what the practical will do this afternoon. You can explore relationships like this between phase equilibria and seismic wave velocities and think about seismic reflectors. You can think about mantle dynamics. You can think about all kinds of things. We use SVD, but I won't say anything more about that. Just one application I'll mention. This is the effect of phase transitions on mantle heterogeneity. Okay? So at a given depth, you move from side to side, the temperature changes, and the relative amounts of phases change. Okay? And so that will be a contribution to the mantle heterogeneity that you see in a tomogram. This is an illustration of that. At cold temperatures, you're going from, say, olivine to wadzleite as a function of pressure. And at hotter temperatures, the velocity of olivine is lower, the velocity of wadzleite is lower by a certain amount. And here's this in-between region where they're coexisting. And what this shows you is that in between, the velocity depends very, very strongly on temperature. So if you plot dV/dt versus pressure, it looks something like this. It has this value here, it has this value here, and then this huge value in between. So you can think of two contributions to the temperature derivatives of these quantities, an isomorphic part that doesn't allow for phase transitions or changes in the amounts of any of the species, and a metamorphic part that ends up looking like that. And so if you look at the thermal expensivity, this is what the thermal expensivity of the mantle looks like of a multi-phase assemblage, a rock, pyrolite, say, density versus depth along two different isotherms, a colder in blue and a hotter in red, and you can calculate the thermal expensivity of this thing. You can actually calculate it more directly with the Hessian matrix, and we're doing that now. But the thermal expensivity actually has all these bumps and wiggles in it. Actually goes negative. You have negative thermal expensivity at the 660, and so on. And we're calculating this now as a function of pressure and temperature. This is the thermal expensivity everywhere in the upper 800 kilometers or so. And you get negative values here at the perovskite forming reactions, some negative there as well, as matrite and ferropericlase form. This is olivine to wadzleite. This is wadzleite to ringwoodite, etc. Okay. Oh yeah, I can't resist. Just one other application. So I've shown you a couple times plots as a function of pressure on the x-axis, and then I've also shown you plots as a function of depth on the x-axis. Okay, how do we get depth in thermodynamic calculations? Well, we get it from Prem, right? Prem is, the density structure is pretty well known. That pressure depth conversion is probably pretty good. But you could also get it directly from the thermodynamics. You can literally build a planet, assume a bulk composition, assume a mass, integrate the equations of hydrostatic equilibrium and the equation of state outward until the target mass is satisfied. That gives you radius of the planet, and it also gives you a pressure-depth relation. And this is the sort of thing that you have to do if you're interested in any planet other than Earth, for which we don't have any seismology, right? Otherwise, how are you going to get the pressure-depth relation? This is the way to do it. And so this is where I've built planets, super-Earths, radius versus mass. Other people have done this too, but I found it very fun to do. This is a pure magnesium silicate. This is the curve for pure magnesium silicate planets. This is the curve for pure iron planets. And these are, as of about a year ago, all of the planets in this mass range for which the mass and radius had been determined. And there are some that fall within this sort of rocky range here. And so you can start thinking about at least the core to mantle mass ratio in some of these planets. Okay. Yes?
So the ones that are up above the curve, those are more gaseous?
More gaseous. These could be, they could have rocky cores with gassy hydrogen-helium envelopes. And one of the interesting things about these, I've also plotted our solar system. There's Neptune and Uranus right there. And some of these are lower density than Neptune and Uranus. So they're so if these guys are icy, more or less, then these guys might very well have very expanded hydrogen envelopes over the rocky core.
What about that denser than iron planet?
Yeah. Well, it does have this big error bar. Sometimes the error bars on these things are quite enormous. There's a paper where people took this seriously, and they said, what if that's actually real? Okay, so one possibility is that it's like a pure uranium planet or something, right? That doesn't seem very likely. The other possibility is that you start with a Jupiter very far from the star, and it migrates in towards the star. There's some evidence that a lot of planets might do this. So a Jupiter starts way out there, migrates in towards the star, its envelope gets blown off, and you're left with just the bare rocky core in the end. Okay, and now we come back to that question we had before about bulk viscosity, right? Now you've got something really big that wants to expand, but might take a finite time to expand. And that's what they actually suggested, is that because of bulk viscosity, it would take a finite amount of time for this now bare rocky core to expand back out to where it wants to be once the envelope is blown off.
Is that as plausible as unobtainium?
Well, I think significantly more plausible, yes.
Just out of interest, if you do the same operation for the Earth, assume like a chondritic bolt composition, how are you orders of magnitude off Prem, or are you quite close to Prem?
Quite close to Prem. It can't be very far off because the densities aren't that far off. We typically match Prem densities to within a percent, so it won't be that far off. Yeah.
So you started off and you said you cannot, well, using the thermodynamics, you cannot predict. But just as a sort of a thought experiment, what was your reaction to, I get it wrong sometimes, phase H or H phase when it was discovered?
I have not read the paper carefully, and I'm very interested to hear what those more familiar with the experiments think. I think it's a fascinating observation of potentially very important geophysically, if true. I'm in some of the questions I have, some of the things I'm interested in learning more about are whether there's any other possible explanation for the diffraction lines that they see. What effect the very interesting multiple single crystal inversion algorithm that they use might have on their results, and what the composition of the H phase is too. I couldn't work out from the paper what they think the composition of it is.
The theory for the thermal part of the free energy was largely based on quasi-harmonic lattice dynamics.
Mm-hmm.
But you very briefly talked about how the Gruneisen parameter changes for liquids. And I'm wondering if there's any corresponding sort of statistical theory for liquids that can generalize.
Very, very limited. The thermal part of the free energy in liquids is much more complicated because you can't reduce it to just lattice vibrations. You have diffusional modes. You have, which you can think of as sort of zero frequency modes of oscillation that don't have a restoring force because atoms are free to just migrate throughout the liquid, and that turns out to be a very large part of the entropy in liquids, even a dominant part of the entropy. So one of the things that people do is they go back to sort of toy models of liquids, like a hard sphere liquid is a classical example. What if you had a sphere of billiard ball? A liquid of billiard balls, composed of billiard balls. What are the thermodynamic properties of that? And what sort of general patterns can you extract from that model that might be useful? And one that people have done some work on, and we have too, is you find that the energy goes not like the temperature as it does in solids, but it goes like temperature to the 3/5 slower. And so the heat capacity ends up decreasing with increasing temperature, unlike solids where it asymptotes to a constant value. And we're finding that agrees with the first principles simulations pretty well. But that's the sort of thing that you need to make progress on constructing a model like this for liquids. All right.